Welcome, everybody. We appreciate you joining us here today. I'm obviously reporting live from a cabin in northern Michigan, as one does. But in this beautiful remote we find ourselves in, here's one of the benefits. You can work from the middle of nowhere in a cabin, and I'm reporting to you from there. So welcome, everybody. Today, we have a very exciting session for you. We are talking about computer vision. So session is Machines Can See, How AI Enables Computer Vision. We're going to be diving into all sorts of exciting topics around how machines, broadly speaking, but how computers can process visual information and react to the environment around them in ways that mimic human vision and beyond. So for quick introduction's sake, for those that don't know me, my name is Jacob Smith. I'm here representing Altimetrik, a digital transformation company based in Southfield, Michigan, with a global presence. When I say digital transformation, essentially we help companies stay ahead of the curve with the ever-changing landscape of technology, source innovation from within their teams, et cetera. And our team members work on a wide variety of things, autonomous vehicles and a lot of exciting things, and data engineering. This topic, one of our speakers here, Antony, who's going to be speaking in just a moment, is a member of our team, and we've been talking about just kind of exciting applications on the AI data side that we can share with you all. And one that he's particularly excited about is this topic here today, which he has particular expertise in. So very excited to share his perspective. And so I'm actually going to go ahead and hand it off to let our speakers to the topic in more detail. But we're excited to be joined here today by Antony Martin, as I mentioned, as Chris Penny, reporting live from Texas. I suppose that they can kind of explain just in a bit more detail kind of what experience they bring to the table, because otherwise I'm going to butcher it. So, and yeah, without further ado, would love to hand it off to Antony and Chris to teach us all about computer vision.
All right. So I'm going to grab the screen, and between I and Chris, we put together a quick deck so that we can, as we're talking about things, we can visually see what the context is. So we do that. Are you able to see my screen?
Yeah.
Okay.
Yep.
Great. So I'm Antony. I am part of Altimetrik, deputed at Ford Motor Company. I work in the electric vehicles area. So Mach-E is one of the product that we are working in, which is going to be rolling off from the assembly. So place your order soon, please. But computer vision. So prior to getting into the electric vehicle, I was working in an autonomous vehicle. That's where I picked up interest in artificial intelligence. And that led me into a learning session. I wanted to learn more about computer vision. So I enrolled in a program with UT Austin. That's where I met my friend Chris Penny, who's tuning in from Austin. So we both have same interests, wanted to learn more about AI and explore in that area. So I'm very much thrilled and excited today to share both our perspective on computer vision. We particularly want to touch on the topic. Again, this is going to be a little bit introductory. So we want to touch on the topic of what computers see, how do they learn, some of the use cases and tasks that a computer vision could do, and what risks do we see with computer vision and how we can mitigate it, right? So those are the questions that we want to address. So with that, Chris, if you want to add something, please.
Yeah, absolutely. So, hey, my name's Chris, tuning in live from Austin, Texas. Like Antony said, we were in the same program at UT. My background is I work for a systems integrator called Mythics. They're based in Virginia, but they've got offices in DC and other spots across the country. We implement cloud solutions, whether that's Oracle or Google Cloud. Traditionally, it's been more, like database workloads and applications, but as AI becomes more common in the business space, but we're starting to do more AI services and more data science services. So hopefully I can bring that kind of business perspective to this. But like Antony said, the goal is just going to be intro level, so it can be kind of the tip of the spear, but you'll be able to use this information to dive deeper, because there's a lot of depth to computer vision. It goes a lot deeper than I think a lot of people realize, and it's not just API fishing, or it's not just throwing data at a problem. There's a whole lot of science and art behind it. So I'll give it back to you, Antony.
Right. So with that, so first, I wanted to, take you guys through like the history of computer vision, right? So the history goes back to like 543 million years ago, right? That's when something extraordinary happened according to the evolution theorist or scientist. So they believe that within a span of 3 million years, there was this rapid explosion in species. They call it as like a big bang of species evolution. And there are many theories floating around, around this topic, but one of the prominent theory is that that's when the species became sensitive to light, which means that they got their eyes, with which they were now able to get their food, hunt their food, right, and then the predators were able to hunt their food, and others they were able to hide from the predators, and the species just evolved, and there was an explosion in the species, right? And another interesting thing to note is that we all know how complex our brain is, right? But I didn't know this about recently, but like over 50% of our cortex, right, processes visual information, and it processes and compared to any other senses, the other four senses we have, like the touch, hear, taste, and feel, right? Compared to all these four senses combined, so visual sensory has like it's a lot more complex, and the brain it allocates like a lot more visual sensory or cortex to just process the visual content. So 80% of what we perceive, right, comes from vision. So this is just to stress that like how important it is, vision is for human, right? So if you want to take this and apply this into computer vision, so before getting there, right? So I want to touch on one more thing, which I think this would help us tie it back to the computer vision. So in our retina, we have like over 127 million photoreceptors. Again, there are like two different types of receptor, rods and cones. Rods are highly sensitive, but agnostic to colors, whereas cones are color sensitive. Right, using these two, photoreceptors, our eyes are able to capture the light and send it to our brain for processing. Right, so all our eye does is it's just the lens where it collects the data and sends it to our brain, and the brain is where the vision is being processed. Right, so we use the term very loosely, like we see with our eyes, but actually we see with our brain. Right, so our eyes are just lens to what we see and perceive.
Right, and just to jump in on what Anthony said,
yeah,
it sounds cliche, but the most impressive neural network is definitely the human brain. And if you think of models are designed to approximate a process, and the process that a lot of these neural network models are designed to approximate is stuff that the brain does, seamlessly, like visual recognition, visual tasks, pattern matching, pattern recognition, things that we do almost implicitly without second thought.
Right. Thanks, Chris. So, so I talked to you guys about like our brain is the one which is processing the information. Of course, as many of you may know, our brain has like a number of neurons or billions of neurons, which takes the information from our eyes and processes it at different stages. Right? It's not just the work of like one single neuron to basically take all the visual information and it gets and then make it or creates a meaning out of it, right? So it's basically collections of millions and billions of neurons that processes this visual information at different stages and brings a meaning out of it. So the main, the AI evolved, at least the computer vision basically evolved with the study that Hubel and Wiesel did in 1959. They wanted to understand how the visual processing work in human brain. So they did an experiment on using electrophysiology on a cat's brain. And what they found out was like they basically bucketed these neurons into 3 different cells, like simple, complex, and hypercomplex cells. I don't know if you're able to see the image on the background. It's very light, but if you see these letters A, B, and A, right, in retina, it's actually inverted. So the simple cells are responsible to, to detect the edges, and then the complex cells are responsible to, represent more abstract information, and the hypercomplex cell, it captures the orientation and where it starts and where it ends, right? So these 3 cells, again, I'm oversimplifying it, but these 3 cells are how the visual information is processed, right? It's not like at one single shot, we see like a human face and we are able to detect it as a human. Basically, it identifies the edges and then understands more abstract image, and finally understand where the image starts and stops. So this is the learning that the community took and applied in computer vision. So they created the models that can first identify edges and creates more abstract information as it goes down into the layers. Eventually, at the end of the layer, a model we would have like a more abstract image. So, Chris, do you want to add anything?
No, I think you hit the nail on the head. I mean, we're trying to replicate a biological process using computers and machines.
Right. So with that, why? So, it's evident that because you guys have dialed in, I'm sure you guys have some interest in computer vision, but why does it excite us, right? This is an interesting question to ask, right? So, so if you see here, so it's a checkerboard, and I hope you have at least seen the checkerboard at some point in time in your life. It has like the alternating color, like white and gray. And I want to bring your attention to these 2 blocks, right, where it's inscribed with letter A and B. And I'm sure most of you guys agree with me that so A and B are on a different colored block, right? However, it's not the case. A and B are of the same color. I don't know let me know if any one of you are seeing A and B as the same color. But I, at least, right, I couldn't, to me, this A looks at like a darker gray and B as like a lighter gray or white, close to white maybe. But if I draw a pathway between A and B, you might be able to understand what I'm talking about here, right? So when I'm drawing a pathway with the same pixel intensity that we have in A, you could see like how that blends with the A and B. Like this indicates that the A and B are of the same luminosity. But why does our brain is not able to see the actual the background color that we have in the block B, right? So just think about it. We will come and tie it back it up when we talk about the actual computer vision model that we are going to be discussing in a little while. But this is an interesting problem, right? Why our brain is not able to see. And to illustrate one more thing, I'm going to show a word. Again, you do not have to come off the mute. Talk it out real loud, and then following that, I'm going to ask a question. And just think about the answer that comes into your mind real quick, right? So the word, right? So if you guys have read it as sharp, so what do you do when you are at a green light? Some of you might have said stop, right? I tried it with some of my friends. They said stop. Again, I tried it with Chris. He was able to get it correctly. He said go. But most of us, at least based on the experiment that I did among my friends, they said stop. That's because we primed our brain with chop, and stop, it kind of rhymes close to stop, right? So our brain kind of related it to that. So we are able to, so what I want to demonstrate with this is that our brain is not perfect, right? We train it, and our brain always, when we see something, we compare it with our previous experience and try to bring an inference out of it, right? That's how our brain learns. When you show a new object, or when you see a new object, right? You always compare it with an experience that resembles very similar to that of what you see, right? Though you may not have experienced this new image ever before. So that's how our brain learns. And that's the trick that we have here, where we primed our brain with the word sharp. And some of you might have said it has stopped, right? Again, this is another interesting thing that our brain does. And what we talked about in these two, this diagram and it's with this demonstration, we are going to tie it back with the neural network model that we are going to be discussing, and will help you understand like why our brain does this, and how our computer vision model is able to draw some inference very similar to that of how our brain works. Chris, again, jump in at any point in time.
Right. To piggyback off that, I mean, our brain uses frameworks to make sense of the world. If it didn't, then I know we'd probably overheat, and self-implode. But it's just interesting how some of the frameworks that the brain uses. And then I think when we get later in this presentation, and when we dive into some of the computer vision frameworks, we'll also be able to see some of the shortcomings of them as well.
Right. So another interesting thing is like the world around us. If you look around your, the room that you are in, it's busy, right? It's full of 3D objects. It's busy, and the objects are occluding each other, right? And our brain has to perceive this 3D world in a 2D imagery, and then make sense out of this 3D world. That sounds complex. Yet alone we aspire that we want computer visions to do something what our human vision does. So that sounds complex and interesting to me. So with that, I want to go to the next stage and talk about what we really want the computers to do, right? So if you see this image on the bottom right-hand corner of the screen, if I ask you to describe it, most of you would be saying like, here we have a family on a beautiful warm day, a mom and two children, a boy and girl. They are happy. They are playing soccer as a family, and you just add this rich information as a human when you see this picture. But some of the computer models that we know that we have now, what it does is like when you pass an image like this, they would be basically detecting and recognizing what the object is. So they may say like, here we have people, male, female, they are happy maybe, they are running, playing, it will just add like bunch of labels to it, but not give the rich information that us as human could do. So if you see this, right, this is very similar to that of what 1 year or 2 year old kid would say. Like when you ask them something, they would basically say this one letter word. They would say like ball or boy, right? They wouldn't be able to describe this rich information. So that is the stage our computer vision field of study is as of today, right? Our field of study is like as of a 3-year or 5-year-old. So we want our computer vision to be able to give this rich information that us as human could do. So Chris, any thoughts?
Is the next slide on what computers see, how they see pixels?
Yeah.
Okay, yeah, we can just jump to that one and we can kind of go into how the computer is able to make sense of it. I mean, humans, we make sense of images like this whirl of lights. Our brain makes sense of it in kind of a black box way, but the way that computers do it is a bit more sequential. And we can get in the next slide on that.
Yeah. So with that, let's take this example of like owl. So this is what we see, but computers see a bunch of numbers behind it, right? So these numbers, these matrices that you see are the pixel intensity of the picture itself. So what we are going to be sharing today is a very basic multi-layer perceptron model that takes this information, processes it sequentially, and able to make a prediction, right? So
right.
here
And this is, I'll jump in real quick, just to tag on what Andy said about the pixels. This is important because most of the image formats and most of the data you're going to be dealing with, if you're doing any kind of computer vision at the image level, it's going to be either like JPEG or PNG. And then you can also do different computer vision on videos too. But the most common format we're going to see is either black and white or RGB. And the way that these pixels are arranged, the way that the computer interprets it, it interprets it as a three-dimensional tensor. So the first dimension is going to be width. The second dimension is height pixels, and then the third dimension is channels. So for the most common image format, that's RGB. So there's three views of the data. There is the red, the green, and the blue channel, right? And the computer uses these pixels. They're usually arranged between 0 and 255. The lower numbers represent a lighter intensity. The higher numbers represent a darker intensity. But the computer will take those pixels. It will do some pre-processing to put it in a format where the model can best exploit it. And we jump into the pre-processing later, but that's just important to understand that you can't just throw data at a model the way it is. You have to massage it, and you have to arrange it in a form where it can be exploited based on the mathematics of the model. So just wanted to make that clear.
Yeah, thanks, Chris. So we take all these matrices and then we flatten it and then pass it to the input here, the input layer. And then if you see here, this input is being sent to the hidden layers, and all these circles that you see here are what we call as neurons. So again, we have multiple hidden layers stacked up here. And then finally, as this input processes through each of these neuron, again, the computer vision algorithm is like spatial hierarchical layer. So it first tries to identify the edges, and then the abstract layer that we talked about a little while ago, how our human brain processes it. So the earlier layers, like the hidden layer 1 maybe, right, in this case, would be able to identify the edges. It would say like, I see an edge here, I see an edge here, right? So that's what these hidden layer 1 would do. And the hidden layer 2 maybe would be able to find some abstract information of like maybe ears, right? Eyes, beaks, or the, the wings, the feet, whatnot. And then as we progress through it, find more and more abstract information, right? Maybe when it comes to this layer, it would be able to identify the entire face, or entire body here, right? Or whatnot. So that's how the computer vision model learns. But what is the learning here, right? So we just have a bunch of number here, and we are passing it.
Yeah, I was going to say, let me jump in real quick. And if you notice, this particular model that's up on the screen is known as a multi-layer perceptron. But I'm going to assume you guys have some background knowledge on maybe simpler data science models like linear regression or logistic regression. The beauty behind neural networks, and neural networks really are the backbone of modern computer vision, is that the architecture is extremely modular, right? I mean, if you're doing like linear regression, or if you're using some of those older methods, you're kind of limited to the functional form of the model. But with neural networks, we can stack additional layers, we can remove layers, we can do other neat little tricks like skip connections or gates. I mean, this is an extremely modular and flexible framework, and I think that contributes to a lot of the power that they have, and why they're so ubiquitous in modern computer vision applications.
Yeah. So the question comes out like, what are we learning? Like, what is that computer trying to learn here? So here on the bottom right-hand corner of the screen, if you see here, I have a bunch of formulas. If I ask you to come up with a number or find X that would be able to answer this question, then you can easily tell like 2 is closer, whereas here it's if 5 times 2 is 10. I intentionally added it here because our computer vision model is not perfect, right? At times it will make mistake, but the overarching idea is like, how can we learn this X value that is able to explain the world it sees as much as possible. So here the X in our model is this W. So all these lines that you see going into this the neurons. So what we are passing here is like the input that we get from the pixel, but along with input, we are also passing something called weights, a random number, which is nothing but an X, right? We are passing an input and an X. And what we are trying to learn is like what should be the value of X at each of these lines that you see that connects one neuron to another neuron, which would at the end of the day would contribute to the prediction. So if you see in this diagram, right? So if I take this image and process it through, at the first turn, like when it takes the image and it comes to the output layer, it would probably predict like a circle, which is totally off, right? Which means that our computer vision model has not learned anything. It just, it's not what we have as an X value was just a random guess. With that guess, we went in and it predicted very bad. So how do we learn that, right? So we calculate a loss. So we know this is an owl, and that's what we want our computer model to predict. But what it predicted was circle. So we calculate a loss, and then we'll try to identify, like, how each of these weights, right, as well the neurons that we have here, activation layer, contributed to the loss. So it's not like if the loss is like, let's say, a value of 1, we are not going to update value of 1 with all these weights. We are going to go back and see, like, how does this particular weight, Wi of 3, contributed to this overall loss, and then update the weight accordingly so that we get a better picture. So we go back, right? Once we calculate the loss, we go back and update each and every single weight based on how much it had contributed towards the overall loss.
Right.
And that's how we are able to learn.
Right. It's like you said, the loss is a single number, and you calculate it over the entire data set, but it quantifies how right or wrong your model is, right? I mean, it quantifies the error. And what we're doing right now is we're doing optimization. So when I say I want to optimize this loss, when I want to optimize this cost, what I mean is that I want to minimize this loss function. So then the question is, well, how do I minimize this loss function? Well, these models have weights, and the weights, they're called trainable, meaning that we can adjust them. So if you think of the model this way, every single layer, the output of every layer is a representation of the data. So like Antony said in the beginning, the simpler layers, the early layers, they learn simpler features, they create simpler representations of the data, right? And that representation is just a weighted combination of the weights and the inputs. And then there's a nonlinear transformation added, but I don't want to get too technical. But as you progress, as you propagate further down the network, your representations are going to be more complex, right? And that means that your model is learning more complex, more task-specific features. Like, in the beginning, it's learning edges or blobs. In the middle, it's learning entire shapes. And then at the end, you can say it's learning faces, eyes, and ears. But the way in which we improve our network over time is that we have to adjust the weights. And they're called trainable because that is what we are adjusting with gradient descent, which is the procedure we use. But I don't want to be too technical, but just wanted to throw that in there.
Yeah. Thanks, Chris. So we talked about weights, right? So the weights are the X's here, and as you may know, like our brains, when it processes some information, like all the neurons does not get fired at time. At time it suppresses some information, and then only fires certain neurons, right? How does it happen? So that's the same. So with our brain, it's actually the electrical pulses, right? That either turns on or turns off a single neuron. So we took the same concept, or the researchers took the same concept and tried to figure out, like, how do we make sure, like, we fire only those neurons that contribute to the prediction and suppress those neurons that does not add value. And they did it by what Chris touched upon a little while ago called activation functions, nonlinear activation functions. So what it does is like it takes like the input and the weights, the product sum of all the inputs and weights, and then passes it to a nonlinear function. Again, we don't want to get into too details. There are a lot of nonlinear function, but this function acts as a gate, and it says like, yeah, whether I want to send this signal down to my deeper layer, or it would say like, I don't want to send these signal, and then it would suppress right here. Chris, any thoughts?
No, I mean, you hit the nail on the head, right? If you look in the corner with that process, it consists, a good way to look at it is it consists of two steps. There's a linear step in which you're doing just a linear combination of the inputs and the weights, and you have a nonlinear step. And the nonlinear steps when you pass that through a nonlinear function. And the reason that's important is because by adding that nonlinear transformation, you can learn more complex patterns in your data, right? If you're only doing linear functions, you're going to be limited in how complex of patterns you can learn. And when we're doing AI work, the patterns that we're trying to learn, because one way to look at AI is just pattern matching or pattern recognition. Some of these patterns are very complicated and they're very complex. So we're going to need nonlinear transformations.
Yeah. So with that, we'll go into like some of the tasks that computer vision could do. So Chris, if you want to take over.
Yeah, absolutely. So this is, we're going to break it into some of the tasks. I guess the first or the best way we can look at this is to do the main dichotomy of computer vision tasks. And that's either going to be classification or localization, right? So with classification, we are essentially labeling an object. We are trying to learn a mapping from an input, which is going to be those pixels, because that's what the computer sees. And then we're trying to map that to an actual category. In the example on the left, you can see that it's cat, right? So the input would be that cat image, and then our model would be able to recognize that's a cat, and then it would map essentially those pixels to the cat output. And then the other task that we are interested in is localization. And this can happen one of two ways. It can happen as a regression task in which we are trying to predict bounding box coordinates around the image, or it can happen as a classification task where we're learning what's called a segmentation mask. And in the later slides, I kind of dive more into that. But I guess all you need to know right now is that there's two main tasks, and then all the other tasks are essentially just combinations of those. But the main tasks are going to be classification and localization. Classification, you want to know what it is. Localization, you want to know where it is. That's the best way to break it down. We've got active areas of computer vision research on the bottom. I think there was a question. Should we answer questions as they come, or should we do it at the end? Just curious with the event coordinators.
Completely up to you all. Usually, I think in this context, it probably makes sense to do them as we go. It's up to you guys.
Awesome. So yeah, here's one real quick. How is the pixel data set organized in the input layer? If this were to, is this where the model would perform some kind of EDA to normalize and transform the data and outlier analysis? So I'm glad you brought that up. On the last slide, we talk about training workflow and we get into EDA, but the pixel data, you would have to do some kind of pre-processing, which would be like normalization. And most commonly with computer vision, that's going to be scaling it between a range of -1 to 1 or 0 to 1. And there's also some other massaging you have to do, but we've got a slide, I think it's the final slide where we talk about those workflows, and there's something on EDA too. So I'll kind of bookmark that for later. But the most active areas of computer vision research, medical, super active, that might be the most active next to robotics and autonomous vehicles. There's that image on the right where they're using computer vision to essentially diagnose a patient. I think they're looking at the chest x-rays, and this is one of the projects me and Antony did in our class or our program. They're looking at chest x-rays, and then they're predicting a map of where the ammonia inflammation is, and then they're going to classify whether this person is ammonia positive or not based on their x-ray. And the reason why this problem was important was because there was a lot of variance in the way that x-ray technicians were doing it, because there was different techniques. This added almost a level of singularity in which you can kind of fact check some of the X-ray technicians, or it added, a second opinion based on what the computer saw. So anytime you have like a really subjective field like that, there is a opportunity for AI to come in and assist. I wouldn't say replace, but definitely to assist. Other active areas, consumer applications. With iPhones, they have the facial scanners now, where you can unlock your phone, and there's other forms of biometric scanners. And then retail, a lot of cool stuff happening in retail with visual search engines. This was one scenario which I think people are hoping to get towards the next future, where you can kind of point your camera phone at like any image, and then it can bring up, I don't know, maybe like an Amazon landing page of that particular product by different vendors. So that's one aspect. Then augmented reality. I know they're doing some of that in the construction space. I think they're trying to do some of that with sports now, where they can do sports simulations based on computer vision. So these are just some very active areas of research. Oh, someone says they used Google to look at a tree the other day and it showed the species. So that's one example of computer vision right now, and consumer applications doing very cool niche things. I think the key though is specificity, just because we get to this later, but the more specific you can be with your problem framing, the better. AI hasn't reached the point of artificial general intelligence yet, which is where it can do, a lot of abstract things. It's kind of like a loaded gun, so you got to point it at the right position, right? It's not like the shooter where you can orient, move around, navigate. It's just a loaded gun, and you want to make sure you're pointing it at the right place. But we can jump to the next slide. So here's two tasks. Image classification, we touched on this on the last slide, but there is, you see to the right, you see what the computer sees, the pixels, right? Or you have, let me rewind. What you have is you have the image, the cat, right? That's what we see. Then when we obviously input this data into the computer, what the computer sees is pixels, but it's learning a mapping of those pixels to a class category. It's really just labeling. And then in the bottom, you have a much cooler task and a much harder task, in my opinion, which is object detection. So this consists of both classification and localization. The model has to detect certain objects that it's trained on. So that's the classification part. It has to label those objects, but then it also has to localize them. It has to find out where they are in the image and draw a box around that. Most modern implementations, what the model is actually outputting are offsets to anchor boxes that already exist on a grid. But for all intents and purposes, the resulting output is going to be a box that localizes where the particular object is. You want to add anything to that, Antony? I know you've done.
No, so some of what Chris is talking about, we'll see it in a use case at the top of the hour. A quick time check, Chris, we have got 15 more minutes, so.
Awesome. Yeah, so the next slide, another two tasks. We have semantic segmentation and we have instant segmentation. These are two very similar tasks. And these are, I talked about the other way you can do localization. One way is with bounding boxes. The other way is actually with a map. So with the map, it becomes more of a classification task. It's called dense classification, but essentially you are classifying every pixel in the image. And when you do that, you're able to really learn the contours of an object. And as you can see in these two images, it's a bit different from the object detection, which has those boxes. This actually has the contours around the silhouettes of their shape. So I think this is it's a bit harder than object detection, but I think it's a bit cooler as well. And we can
I feel like this is much more precise localization coordinates, because we're able to identify or classify every single pixels. So that way we know exactly where in the picture a pixel falls, and we will be able to draw a bounding box or coordinates with a better accuracy compared to the object detection.
Right. Let's jump to the next one. So we have another two tasks that I think are really cool, and these ones are maybe, I don't want to say underground, but they're not as well known as the first four. And this is the first one's going to be similarity learning, and that's most commonly used in facial recognition and facial verification. But what essentially you're doing is you're taking an image, you're extracting a feature vector, and a feature vector is just a two-dimensional embedding from that image, and then you are comparing that feature vector to, let's say, other feature vectors in a database. So if you're doing something like a facial verification, you would have a feature vector representation of everyone's image in your database, and then when you have someone new, you would scan their face, you would generate a vector, and you would compare those two vectors. And there's different ways to compare it. You can do either distance or similarity, but that's kind of diving more into the mathematics of it. The way we see this being used now, we see this with facial verification. We also see it with speech verification, and we see it in a few other cool niche applications. The one on the bottom is landmark detection. So this is a regression task. And what you're doing is you're training a model to recognize specific landmarks on a person. So if you're doing facial landmarking, you're training the model to recognize the coordinates of the corners of the mouth, nose, eyes, other distinguishing aspects of the face. But you can also do this, you can do pose estimation, in which you're training the model to recognize the coordinates of joints. So these are another two very, very cool tasks that I think are super neat. And can you go to the next slide? Okay, I know we're short on time. Do we want to go through this entire UNet architecture, Antony?
No, but at a very high level, because we are going to be what Chris talked about, like the object localization, and then this similarity detection and the unit architecture that you're seeing here. All of this is going to be used in a model that I'm going to be sharing in a little bit. But yeah, go ahead, Chris, if you want to touch at a high level.
Yeah, so from a bird's eye view, this is an example architecture. And the reason I chose this one, it's commonly used for biomedical images. I chose it because it's beautiful looking. The fact that it's symmetric, you won't always see that with other models, but don't let its symmetry kind of hide some of the things that are happening underneath the curtains. I know when you open up its kimono, you'll see a lot of cool things that are happening. If you look on the left side, that's the encoder side. That side is really designed to learn the what, right? So it's called downsampling, and what the encoder is doing, it's really learning the what, right? It's learning global features and the what of the image for the classification task. Then you have the right side, which is the decoder, also called an expansive path. That's learning a lot of the specific local information. So I like to think of it as the left side's learning the what of the image, but the right side's learning the where, like where are these pixels, because it has to draw that segmentation mask. Right. And then we'll jump into, there are 2 or 3 use cases. I'm going to kind of fly by these, unfortunately, because we're running low on time. But one use case, which I've done before, which is really cool, it's a real estate pricing prediction model. And what it does is it's a 2-headed neural network. One head takes, let's say zip code, listing, other kind of attributes, other data you can find from any like MLS listing. And then the right head takes image data, so image data of the housing. And I think there was 4 images that were used: the bedroom, bathroom, kitchen, and the outside of the house. And what you're having on the left, one network is operating on the tabular data, and then the network on the right is operating on the image data, and then it's going to concatenate and combine the outputs of those 2 networks. And then you have a final layer, which is going to predict the housing pricing, or what this house will go for on the market. So this was a cool application of how it's being used in real estate. We have another application, which is maybe a bit more topical, considering COVID, but this researcher, and I'll link his information at the end. I think he's got a lot of cool use cases. And like I said, I'll link his information at the end. But they did a project where they were predicting whether a person was wearing a mask or not. So they trained the model on this data, which you see, and on the right. So the training data, some images had people wearing masks, other images had people wearing no masks. The final result was that the model was able to predict whether a person has a mask on or not. So obviously, the most immediate application of this becomes like surveillance. you being able to detect if someone has a mask or not. And we can jump to the next slide. Another two cool applications, and these use the landmark detection that I mentioned in a few of the slides back. One's an emotion detector using facial landmarks. So again, it's learning the coordinate positions of those eyes, nose, corners of the mouth, other landmarks on the face, and it's using that to classify what mood the person's in, which I think was really interesting. And then you have the pose estimator, which is where landmarking is being used for like a fitness app. So in this case, the landmarks aren't on the face, they're the joints of the body. So and you could have like a personal trainer application, or even like a dancing application or something where you're able to track this and give feedback to the person on how good their pose was or how right was their form. So these are two use cases of computer vision.
Right. And I want to add quickly one more thing. So these use cases that we saw are like mostly that the data-based AI, where we train the model with a bunch of data. You could still sense that it's a machine. But there is another system called the knowledge-based or the expert AI, where the human-machine interaction is very less. You almost feel like you are talking to a human when you are interacting with an AI. Just imagine like if we are able to now, I think our AI is still a toddler, but if the point when it becomes an adult, right? Just imagine the kind of use cases that we have. Like we could do deep sea exploration. We could do deep space exploration where the human cannot go. No, we do not have to just send a Mars rover, right? We can send a robot that is very similar to that of a human, which can see things and describe the rich information that we would describe as if we were in Mars. So that the use cases are limitless. But again, this is still a very much evolving field. We are still in the early day of its maturity.
Right. So what's the next one? The next one is, I did want to talk about some gotchas. I'm probably gonna have to run through these, unfortunately, because of time. But making computer vision application isn't just as easy as throwing data or doing API farming and fishing. One reason or one way in which the model that you train might not perform good in production is that if you're training data and your production data are coming from different probability distributions. What I mean by that is that if you're training your data on like high quality images you got from online or from like a professional camera, but your actual application and production is like a mobile app, therefore the images that it's going to be processing come from mobile phones. There's going to be a difference in the quality of images, probably a difference in the size of images. They're essentially coming from the same probability distribution, but with different parameters. So you're going to have a mismatch between how your model performs in the lab on the most high quality of images versus how your users use it in production. Another issue is data leakage. This can inflate the performance of your model in the lab. And what I mean by that is this happens when your model has access to information that it wouldn't have in production. So if you have a lot of duplicates in your training data, which is called sample contamination, or you have maybe some of the same examples in your training set that are in your test set, then your model's gonna overfit to those examples, and it's gonna look like it's better than it really is in production. And then maybe the biggest issue is data bias, and this is super important. And this is that everyone kind of assumes that data is this ground truth, but you have to really consider the way in which data was collected, right? What are the data collection methods? And you'll realize that the data collection methods usually represent some greater social context. So in the sense of like that real estate prediction model I talked about earlier, zip codes reflect a lot of real world bias between like different ethnic groups or different minority groups. And what can happen is your data can learn and pick up this bias, right? So if your data set was, let's say, it's only trained on like people from one particular ethnic class, then your model will not be good at different ethnic classes in production, right? That's one example. Another example would be you have imbalance classification. So your training data consists of like 99% of one class and 1% of the other class. your performance might look good, but then once you get in production, you realize that your model just learned at predicting one class really well. It didn't learn at distinguishing between the other class. So data bias is probably the biggest issue to why some of these computer vision applications and some of these NLP applications haven't probably hit the mainstream market yet, or even why some of these healthcare applications, you don't see them as common as they could be. And that's because of an implicit bias in the data in which certain groups are underrepresented. So I wanted to touch upon that because that's the biggest, one of the biggest challenges to the adoption of AI at the moment.
Yeah.
And,
So
and just to chime in,
sure.
Sorry, Anthony, just to chime in really quick. What Chris just mentioned is a hot topic of discussion in Detroit right now with the Project Green and police using facial recognition to deter crime and different things. That's a real hot button issue. So it might exploring the bias side of it. It might be a great topic for us to dive into in an upcoming session.
Yeah, I agree.
Agreed. So that's what I want to touch upon as well, the bias, right? So the most recent, if you want to learn something out of the most recent evolution that we had, right? Internet, right? That changed the face of the earth as we know. But when we had the internet, everybody thought that this is the cool thing. We'd be able to talk to people. It's going to change the world for better. But what we did not understand or were able to predict was the vulnerability it would introduce. That we would have never thought about all the cyber threats we have and how much damage it could do to a person or an economy or to a country, right? So if we take that learning and if we apply to artificial intelligence today, like we do not have any governance on artificial intelligence. That being, like, this is not being led by government, right? Most of the innovations in the last century were done by governments, right? At a research lab somewhere in a government facility to protect the nation, and the outcome of it, that is what was available to general public. But now if you see with all these tech giants, right? So this one cool statistics that I found was that the top 5 defense contracts annual budget is less than 50% of Microsoft research funding. So in this century, the tech companies are leading the innovation, unlike government. So that there is little to no governance with these big tech giants, right? So how do you bring about these biases, right? How do you minimize those biases? So that's, or who owns the bias? Like if you train a model to Chris points, and if it is biased towards an ethnic group or a community, who's responsible for it? Is it the person who wrote the code, or the company that is using, or the person, a company that sold, or the person that is using, right? Who is responsible for all the liabilities? I think it's all. So one thing that we gotta make sure is, like, the data is, building model is only 5%. That's the simplest part. Augmenting data is the toughest thing. And how do we augment data is the biggest problem, right? So when we collect the data, it has to be diversified, both physically and cultural diversity. Both of those should be accommodated when we collect the data. Because remember, computer vision is just like training your child, right? If you show them like only a specific object and tell them, like, anything round is a ball, then when he or she sees an apple, she is going to call it as a ball. That's what computer vision is. So if we inherently introduce bias into this network, like if, for example, if you only do facial recognition with Caucasians, let's say, the model is going to be biased towards it, and they will not be able to recognize other ethnicity groups. So it is very important to have a diversified group of people collecting the data and manifesting or providing it to the artificial intelligence model. With that, I want to quickly jump into, I know we are running short on time, quickly jump into a quick demo. So this is called CM Mask. I want to touch on a couple of things that Chris talked about, where the similarity network, where he showed like there are 2 faces and we'll try to identify how similar they are. And he also showed you this unit architecture where the architecture was able to find what the object is and where the object is. So we are taking those 2 principles and applying it in this model called CM Mask, where we are basically taking an image. For example, this is the larger image, and we want to do object tracking. So Chris touched upon object detection and object classification, but this would be called object tracking, which kind of leverages the other 2 that he talked about. So I'm going to quickly show you the demo. So here we have, I forgot his name. Shoot. What was his name, Chris?
It's not Beckham, is it?
Yeah, Beckham. Yeah, thank
it
you.
is Beckham. All right, yeah.
Yeah,
Bennett like Beckham.
yeah, thank you. So he is on a beach, and again, I'm going to fast forward it. He's trying to hit a ball to land it in 3 trash cans. Right, and what we wanted to do was like, just track David across this video. And just draw a bounding box around him and have it segmented. Again, this is done using the CM mask. I used the author's GitHub model to make it happen. So if you see here, this was the outcome. Quickly fast forwarded to where he hits the ball. All right, so the application of it would be like in disaster recovery, right? If you want to identify like people who are stuck, or in case of disaster recovery, if we want to do surveillance, right? This technique could be used, and we would be able to precisely tell where a person is and what he's doing. I'm sorry, I would really like to dive into this model and all this stuff, but in the interest of time, let's move on to the next slide. Chris, do you want to touch upon the workflows?
Yeah. And I'll have to probably get this one pretty quick, but there's, I would say that there's 3 main workflows. The first workflow is going to be the pre-training workflow. And really the start of any problem is going to be the problem framing. One way I think is an effective method is to think of how you would solve this problem without AI. So maybe using heuristics or using some other method. And then after you've kind of figured that out, then you can ask yourself, okay, well, how can we use AI to do this problem better, or to automate certain aspects of it? And then once you frame it like that, then you can move on to the next step, which is data collection. So data collection, this is one of the more time-consuming aspects of it. You would either essentially have to collect your own data. So then the question is, well, does this data exist online? Is it on like Reddit, Kaggle, GitHub? Or are there other data sets that I can leverage? Do I have to go out and collect my own data set? Depending on what the problem is, that could be very expensive or time-consuming. Can I scrape the web? Can I scrape the internet? And then if you can't collect maybe enough data that you need, well, then you have to ask yourself, okay, well, there's other techniques that have been developed where I can kind of circumvent this data collection problem. Will I have to use transfer learning? That's one technique. Will I have to use semi-supervised learning? Will I have to use hard parameter sharing? Will I have to use, like some kind of pre-training on an unsupervised model? Those are different methods that have been designed to limit the burden of data collection. But generally speaking, neural networks are very data hungry, and they're very computational hungry. So to make the most of them, you're either going to have a large data set, either someone else's or yours, or you're going to have to use one of those techniques I just mentioned to kind of circumvent that. And then we get into the next step, exploratory data analysis. This is where you're visualizing the data, looking for certain patterns. There's different kinds of EDA. There's more of like the business analyst EDA, where you're just looking, where you're identifying the patterns yourself in the data, and you're using that for business insights. There's like product feature EDA, where you're looking at the way that people use your products and use your features, and you're using that to iterate to your value prop. And I think there's a post-processing EDA in which you do exploratory data analysis after you've made your model to debug it. That's the pre-training workflow, right? And then you have the training workflow, which is next. This is where you're actually fitting a model. This is where you're constructing a model. And that's going to start off with data loading. either from the cloud or on disk, wherever you're keeping the data. And then the next step is going to be pre-processing. That is where you have to arrange the data in a format that can be best exploited by the model. In the case of images, this is usually scaling the images, using like normalization or standardization. This is also might be resizing and reshaping the images. Those are some of the two most common things that you would do in pre-processing. Then you'd split the data between your train set, your dev/validation set, and your test set. You train the model on the train set, which means that the model is learning the patterns of the training set. Then you would evaluate the model's performance on the validation set and on the test set. Usually, generally speaking, you're going to be constructing multiple models. So you're going to want to compare the performance of many models. And also you might tune some of the settings of the model, and you're going to want to compare the performance of the same model with different settings. You would use the dev set and you would use the test set for that purpose. The test set is supposed to give you a proxy of production data, but there are some nuances, and this is more of the art in which you have to arrange these data sets so that you don't suffer from the data bias problem, you don't suffer from data leakage, and so you don't suffer from overfitting, right, which would give you an inflated expectation of your model. You think it's doing better than it actually really is doing. Next steps, the training. I think we talked about this in the first slide of how that network works. We tune those parameters until we get the lowest cost on that loss function. You have a post-processing stage. That is usually where you're taking the model output, but you're converting it to an output that you can do error analysis on. One example is like, if you're doing multi-class classification, the model output's going to be a vector of probabilities for each class, but you're really only interested in the class with the highest probability because that reflects the model saying, hey, I am most confident that this particular input is mapped to this class. That is why I have assigned it the highest probability. There's model evaluation and diagnostics. This is super important. This is as important as model building, is how you're evaluating it. Whether it's overfitting or underfitting, whether there is a variance problem or a bias problem. That's essentially how you would kind of navigate model error analysis. And then you'd save the model parameters and you save the architecture either on disk or in the cloud. And then, once you've deemed a model acceptable for production, you would have to capture the data, maybe from like a mobile phone. You'd have to pre-process that data. So you need to and use the same pre-processing steps you use in training. You want to make sure that pipeline's the same. You would load the train model from, let's say, the cloud. And what I mean by loading the train model is that you would load the parameters in the architecture, and then you'd use your model for prediction and inference. You would do some post-processing. In the case of object detection, the model is going to predict the coordinates. You'd actually have to draw the box on the image or on the video, or in the case of the segmentation masks, the model will output the segmentation mask, but in the post-processing, you're actually applying that segmentation mask on the image, and then you'd make decisions based on the result. So, and you want to add anything to that, Antony? I kind of went through it.
No, I think you covered it well. And I'm sorry, everybody, we are over time, like 9 minutes over the top of the hour. So Ryan, if you want to, or Jacob.
Yeah, no, thank you. Just want to say thank you. Thank you so much to Chris and Antony for sharing so much incredible information in such a concise presentation. This was fantastic. So just a reminder to everyone, we will be following up. I just dropped in the chat. We would love to hear from you. So if you have any ideas for topics that we can build on that you'd love to hear about, please do let us know. This video will be sure to subscribe to follow Collider Detroit on YouTube. I dropped the link in the chat here as well, so be sure to subscribe. This video will go live in the near future, next couple days here. And I mentioned that Antony also did a recent session on taming big data for decision making that I think does build on this in some ways. So check that out as well. And yeah, really, really excited to keep on this. This was excellent, Chris and Antony. Thank you so much.
Yeah, and I'm available. I can stay on the call for maybe another 5-10 minutes if any of you guys want to have any question. Chris, how does your schedule looks like?
Yeah, no, I can stay on for 5 minutes, 10 minutes.
Sorry.
Any questions?
Okay.
I have a question to kick things off. Why, excuse me, like why model after human vision? So this might be a dumb question, but like I'm thinking like, like dogs can smell humans. Is it necessarily true that like that the human vision model is the best way to do it? If it's kind of like zooming back and thinking like, what would be the best way to process visual data? Is why after human vision? Out of curiosity.
Yeah, I can take that question. So human vision is superior compared to other species that we have. Example, I believe dogs have only 2 channels. Like it can only, we have 3 channels, right? Earlier in the discussion, we talked about like how we have like 127 million photoreceptors in our eyes, and there is one receptor called cone that is responsible for color sensitivity, and it has like 3 colors zones, like red, green, and blue. Whereas for cats and dogs, I believe they only have 2 channels. So they do not, see the information as we do. And our vision is like much more richer. And that knowing that, we are building this model basically to help us as a human progress. As being in the top of the food chain, if you will. So we wanted to model something that closely mimics us so that we can perceive it, and there should be a way to control this model itself. If let's say if we build something off of the dog's vision, right, we may or may not understand completely of how the dog sees in the real world, right? We can assume certain things, right? We can theorize, but we can never experience it. But modeling something out of human vision, not just that we are superior when it comes to the evolution, but as well like we can assess if the artificial neural network with respect to computer vision is doing what we are expecting it to do, right? That's another aspect of it. Chris, if you want to add.
Yeah, I would say that I think the first neural networks was maybe like the 50s, and I think just modeling it after humans seemed the most intuitive. Same with convolutional neural networks and computer vision, which didn't really, blow up till maybe like 8, 9 years ago. But I think that modeling after humans was the most intuitive at first, and it also gives you the best feedback. Just because we speak the same language, it'd be hard to maybe get feedback from a dog on, how good of an approximation is this for what you see. But I will add though that a lot of the neural networks, though, even though they started off, I think, rooted in that human concept, they've really kind of spawned into something on their own now. And some of the stuff, at least some of the latest research that is happening, it doesn't mimic what humans would do. That was just a starting point.
And also,
go ahead.
I'm thinking, so you just made me think like you're talking about the processing side of the equation. So like, there's no reason these models couldn't see in, for example, like a wider bandwidth of light, like they could see in like, infrared or something, but it would still be processing the data in a way that the human brain would process the data, if I'm understanding correctly. Like it could have like way higher resolution than a human eye, but the point is how the data is like being processed.
Exactly. Yeah, I think that was when they modeled it. I think that was the goal, is to construct something that would process data kind of similar to how humans would do it. So I know that was their creative muse, but it's really kind of spawned into something of its own now, and it's doing things that human processing wouldn't do, which is interesting.
Got it. Thank you. Yeah. And thank you so much to our wonderful presenters here today, and we really to hopefully connecting with you all again soon, but also everybody who's tuning in. See you again in the future. Don't be a stranger.
All right. Thank you guys
for having us. Yeah, thank you.